Hello, welcome to one more lecture on our fundamentals and biomedical application of quantum science and engineering. I am Vanderlei Bagnato, and together in this course we have Professor Yakovlev. Okay, so as I told you in the general first lecture, the first thing we're going to do is try to convince you the importance of quantum mechanics, and then we're going to start the concepts. So my lecture today will concentrate on give you some ideas about the importance of quantum mechanics, right? Tell you a little bit about where to look, how comes around things, where there are some things in quantum mechanics that violate our present intuition, and we have to incorporate that in our intuition to be able to understand things, right? Because when we look something, we come with all the concepts we have. Oh, okay, I understand well this. But now we have to introduce new concepts for you. So first of all, I want to show you where this is important, some general aspects. So this is like a motivation lecture. You know, the first one I gave you was the structure of the course. Now I'm giving you a motivation. You know, just a general, you know, like a colloquial type of introduction. Okay, well, you know, nature is made of atoms and molecules and light. You know, we have light, and we're gonna see that light is made of particles too in quantum concepts. And we look around and in science, we observe nature in many aspects, right? The astronomer are observing the planets and the universe and what they can learn from there. They can make correlation of space-time and try to understand when things begin, how begin. And so we are always observing nature. And we try from that to extract truth. And that's how concepts and theory are constructed. Observation, thinking, reflection, establishment of concepts. You know, many millenniums before, things were based on mind, the man mind. We believe that is what we call domain of philosophy. And the science before, right, science and philosophy were very much connected. We always connect with philosophy because philosophy are kind of concepts we create by our mind that somehow are truth too. But before, you know, they didn't care about observations really, you know, deep experimentation. No. They only care about general thinking concepts and explanation. And we all know the schools that we have of very, very important thinkers on the ancient age that gave us very important concepts, philosophical concepts that many of them even survive today, right? And I think that was before. But then we learn to do science based on experiments. When we learn to do science based on experiments, a lot of things change. Really, you know, because when you think about an experiment, you're not really only thinking about what you want to observe, but you are prepared to observe something that you did not think. And that's when the secrets are revealed, is when you organize experiments and you do the observation. And of course, we're always looking for something. We don't start an experiment without knowing what we go. We never start a trip without destiny. Well, some people do, but most of the people don't. Here is the same, right? The man history in terms of science concept is like a trip. They always want to find something, but they find something else. And one of the something else they discover is the microscopic world. You know, before man creates some elements, you know, the fire, the ground, the earth, and many things that they put together, the heat, or the hot and the cold, you know, the humid and the dry. So they created concepts that are fully macroscopic, because that was the only thing they knew. Nobody knew what was making things, even though the Greeks, they had a good idea that atoms should be there, right? We all know this, even the word atom is Greek. Okay, but then when they discovered really that there was a world that we don't see and are responsible for the things that we see, which means we are what our micro world determines us to be. The constitution, the way atoms and molecules are together, and when they go wrong, you develop diseases and everything. And so when people discovered there was this microscopic world, a very tiny world, then the things change. We start to look things in a different way. It's like looking to the sky, but I'm not seeing only the blue. I'm seeing the molecules that are there. And why is blue? What's making the sky blue? You understand? So the discovery of the world in tiny scale, or what I call the microscopic world, changed the way man conceive things and they think about, right? And here is where the quantum mechanics comes. Here is where, evolving these concepts, it is where the things were important to change concepts, and the quantum mechanics concepts start. But let's step back once and go to the classical world, because as I told you, the universe around us is a mechanical universe. And on the 17th century, a very important British man, Isaac Newton, a monster of science, a monster of thinking. We all wish that Isaac Newton had 3 lives. If he could live like 1.5 century, I think science would be different today, because Newton is clear was one of these pieces of human mind that made the change. And Newton knew the movement of things. And, everybody knew concepts of movement, intuition. Everybody knows that if I touch somebody, somebody goes to the other side. But Newton was in some sense, able to formulate in just a few, truth that governs everything. And that's the concept that we normally look for to establishment of a new interpretation or a new theory of things. And, in the theoretical framework to explain how things move, Newton was a master. He was able to really do things that survives even today. Very little things. I think the mechanics and the electromagnetism are things that made our mind, made our lives change a lot. So Newton, what he was doing is he's trying to combine a few things and explain why objects move. So here's an object on the concept of Newton. And the first thing is he had to create a way to know where this object is. And that's the concept of position. So Newton came and said, well, I have an object, and if I want to understand and describe this object, I have to know where is it. So it came with the concept of position. So you have a physical quantity that's called position, and is able to really show where things are. And for Newton, if you want to understand the past and the future history of an object, a movement, an object moving, planets, anything, you must know what's the position as a function of time. And the evolution in time of this position describe what we know as trajectory. That's an important concept in classical mechanics, because the trajectory going from an initial point to a final point is very important, it's fundamental. And knowing that, you know everything about the movement. When there was an external agent making things to change, everything. So Newton got the right tools, the right concepts, the right quantities to describe one of the most important equation in the classical mechanics, which is the relation between the external causes of movement, which is the force, the ability of one object act something on the other, either by contact or by distance, the intrinsic property of the object, which is its mass. A mass of an object is something belong to the object itself, and the consequence. The consequence of an external act or an external agent acting on an object, and the object itself, when you combine that, you have as a consequence a measurable quantity, which is the acceleration. And Newton was able to formulate that way, or to put together this. He never deduced that. I'm going to show you during our course that using quantum mechanics, in some situations, we can come with this. We can come with a concept that is exactly the Newton laws. And then I'm going to show why the quantum mechanics collapse a little bit to the classical mechanics when we look to the averages of some special conditions. So we can do that, but we cannot deduce quantum from the classical. Okay, and Newton formulated this in a very nice way, which means if I know how things vary with time, which is the concept of derivative, we can create an equation that knowing the force everywhere and every instant, and knowing the properties of the body itself, we are able to tell where it comes and where it's going to go. Even today we apply this. That's why we predict when a comet will come and everything based on classical mechanics. So Newton made a revolution. But if you ask, why Newton put together this? Why? He deduced from first principles? No. He observed, and then he established this. And then he created the concepts. He created the concepts in a way that we use even today. And that's going to happen also in quantum mechanics. We're going to create concepts that works well. Why is that way? Why Newton did not put a square here? Well, he has a reason not to have square. It has to be a linear equation, and he knew that. We know why. We can even prove that it has to be linear, those things. But, that the force is the mass times the acceleration is something that Newton proposed on observations. He said, being that way, we explain a lot of things. And then this is one of the Newton's law. And the second law is about the mass itself, which is about inertia. And even today, we are looking for the difference between the mass that appears in this equation, which is called inertial mass, and the gravitational mass, which is the mass responsible for the gravitational attraction between two objects and everything. Right? And Einstein start to explain and help to explain if there should be any difference between inertial mass and gravitational mass. Gravitational mass is what you measure in a scale, and inertial mass is what obeys this law. Okay, so you see, even the best law of mechanics we have, it was built up in observations, and there are many ways of describing this. You can use the energy concepts. We learn in elementary mechanics that, it's better to explain this in terms of energy and work and momentum variation. So we combine like the space variation with the intrinsic property of the object to create the concept of momentum. And we also combine the variation to create the concept of energy. And sometimes instead of writing the Newton's law, we write in a different way. And many people learn to do that in different ways. And mechanics in general was put in different contexts, in different quantities, but it's the same mechanics. We know what we call Hamiltonian, which is a way to describe the mechanics. We know the Lagrangian is another way to describe the same mechanics. They all come with the same thing. And sometimes we needed to put in that context, instead of speaking about force and acceleration, it's nice to speak about energy, because we learned that when we know things that conserve, the conservation laws, it's easy to deal with the problem. Conservation, and that when momentum energy came about, because those are quantities that conserve. If we try to speak on everything about position, sometimes it's hard. We can't do it because this is fully self-consistent, but it's hard. Therefore, we sometimes needs to express the same law in different ways to understand. Well, almost every moving macroscopic body obeys Newton's law. That's a fact. And thanks to that, everything works around us, and we know what's going to happen. We know how to draw a road so we can make the curve. We can make the turn in high speed. Everything related to the Newton's law. So learning the Newton's law seems that we understand how to use it, and then we can make the life around us easier. Okay. But then we, as I said to you before, we went to the small scale world. The world where we look around and we see not the macroscopic objects, but we see the tiny parts of it, the atoms and molecules. And as the science progressed, people were able to go and test that part of the nature. Go to the microscopic world. When they went to the microscopic world, they found something very strange. Was a frustration that when they went to the small scale, because the idea is, if I understand the tiny little brick that makes everything, I understand everything. Oh, which is true. If you understand the properties of the tiny little things that makes everything, you understand everything. But then they come to the surprise that when they went to that tiny little world, tiny little atoms getting together, giving the object in the macro world the properties that we see. Classical mechanics work in the macro world, but not in the micro world. They could not really explain how things were stick together. Imagine, we learn from electricity that the two charges of the same sign repel each other. A neutral charge doesn't matter. And now we go to discover the nuclei of the atom. And here comes a lot of protons together that are positive. How they stick together? Something is missing here, right? Classical mechanics was not the only thing that could explain things. They should go beyond. They need a new concept. And then they found that the properties that the tiny little world, and we're going to understand why inside an atom, or on the scale of atoms and molecules, is where quantum mechanics reveal more strong. But that doesn't mean that we cannot predict what we observe in the macro world. And when we make a theory, we cannot make a theory that explains something and doesn't explain the rest of it. We have to make a theory that explains what was already explained, plus what the previous theory cannot explain. And that's the quantum mechanics. We just went more broader. We went in a way that we cover much more, but changing the concepts. Okay. So they discovered that classical mechanics that we know, the traditional one, as I explained from Newton, could not explain the observation. When we see the behavior of an electron, when we see the behavior of an electron in an atom, when we see the behavior of two atoms getting together, we could not explain using classical concepts. There was a necessity of a new theory. It's not a new theory that goes and put an extra term on Newton's law. No. It was something else. was something completely different. We could not correct Newton's law to explain the existence of the atom. That's basically what's happened. We could not correct Newton's law to explain how an atom exists, right? So we have to substitute that. And does not complement. I wrote this phrase because I think it's the truth. You know, quantum mechanics do not substitute, do not complement classical mechanics. Substitute it. It's just replaced completely. But we should not destroy the observations of the classical world. Doesn't mean that by introducing the quantum concepts, we're not going to be able to explain what we observe by naked eyes, right? So I hope you got the context. You know, we could not use classical mechanics the way it was to explain, and there was no way of fixing it. We have to come with alternative, you know. And your human mind is so fantastic that sometimes you learn the way that some people think, and you get surprised. You say, how that guy came with this idea? How was his mind? Where was his mind? It's not, we know that we don't know the mind. And I think mind works in a quantum way because, it's so wonderful. It's so, basically unlimited. And then we use only a little bit of our mind. Can you imagine when people start to really get close to 100% of use of their mind? That would be fantastic. If that's used for the good. We know a lot of people that has good mind but use for the bad. Okay, so quantum science, it came about to explain the things that classical fails. And do not correct classical, it's just produce a new concept. That's why it's hard to, you are born, young kid, you learn the classical concepts by intuition. You learn how to kick your friend, you learn how to kick a ball, you learn things like this. You learn how to nail on the wall, you learn all kinds of things that mechanics help us. But then we develop intuition on that. And then I come and say, look, for this word, when we're going to deal with quantum effects, forget about. You cannot use that. Then you say, what? I can only think about that. And that's why we're going to try to change a little bit this intuition, the way you think. You think it's easy, but it's not. It's not because Feynman, the great physicist, Richard Feynman, he said a very important phrase. He said, I think I can safely say that nobody understands quantum mechanics. Wow. What are we doing here then? Nobody understands quantum mechanics. And I think if Feynman even go beyond, he say, if somebody says he understands, forget about, don't pay attention. What that means, right? Means that everything we do is magic. What Feynman, a very respectable scientist, wants to say with this phrase, I think I can safely say that nobody understands quantum mechanics. Well, let's see what he means by that. And of course, this is my own interpretation. What Feynman wants to tell us about that. He wants to tell us, it's not that quantum mechanics is not valid or anything like this. He just wants to say that we don't know why nature choose to be that way. We have no more fundamental principles to build that up. Not yet. So I think that's what Feynman said. Man is not yet prepared for understanding why nature is quantum. And I think that's what Feynman wants to say with that. If we don't understand the whole basis why nature has to be that way, we can't. Some people say that this is in the origin of the universe, the way that before fluctuations, waves and everything, matter has to have that on it. But This is remaining to be understood. And then what we do? We close our book and go home because, since nobody understand very well. But remember Newton, nobody understood very well why F equal to ma, but people use it. Can you imagine the war on the 18th century? People calculating the trajectory to reach the enemy with bullets and projectiles and things like this. They use it. And that's what we do. We don't understand everything, all the basis, why nature is that way, but we observe that it is. Therefore, we learn how to use. We learn how to formulate using the elements that we have. Maybe in the coming future, people are going to change the way you formulate quantum mechanics, right? And then maybe we will introduce different ways of dealing with that. But at the moment, mankind construct the best they could to make that happen. Decades ago, here comes something interesting. And even today, some physicists, before many, they expend a lot of time trying to understand why. Why is that way? And normally they use the concepts they have, statistical mechanics. Even there was a mechanics called stochastic mechanics, which was trying to replace quantum mechanics concepts by making some statistical type of treatment, still using classical. They did not succeed. By decades, people expanded their lives. I'm not saying they spoiled their lives, they expanded their lives, tried to understand, but very little progress was really achieved. And today, we mostly, and then we gave up a little bit about this. Not totally, still many people worry about, but the progress, to tell the truth, is not so significant. People try to understand the things that maybe we are not prepared yet, right? And today, it happens that today, we learn the concepts, and we mostly use it. Learning how to use it, we can do a quantum revolution like the mechanics did a mechanical revolution in everything. All the industrial revolution was done based on mechanics, basically in thermodynamics, but using mechanics on it. Even the thermodynamics grew up using the concepts of classical mechanics. So what we do today, most of us, is to use the concepts of quantum mechanics to advance science and technology. And we're doing very well, believe me. We're doing so well that today we think that we are already in the century of quantum. Age of quantum concepts, because we are learning to use better and better. And I believe that if we keep that way, if we keep learning to use better and better in many fields, like biomedical engineering, like computer science, like everywhere, including physics, of course, we have a good chance to improve a lot the concepts we have. Okay, but a big but is not magic. Any scientists do not believe in magic. It's not something that is complete, no understandable. No, we do need to go back in the future and must invest more in understanding the fundamental. Everybody believes that we're going to find tools that will help us to really understand the fundamentals. But up to now, try to adapt things, try to use what we have. It seems that do not introduce a lot. So you see, the quantum mechanics is something that we learn, some concepts, and we use it. We don't try to question why God made a way, why this, why that. We are not in that stage. So, and I think that many students get stuck with quantum mechanics because they start to question, which is natural. But let me tell you that we are in a stage more to use the quantum mechanics than to understand the really deep fundamental aspects of it. We should go back to that. Maybe now, I see that we are evolving very fast. We are already understanding gravitational waves. We are understanding so many things. We are understanding the fundamental of the mass formation, the Higgs bosons and everything. So we should, in the coming future, have elements to go back and question the fundamental and really make improvement. But so far, that's not really happens. Okay, I spoke a lot about how the things are happening, but let me give you an example, which is the failure of classical mechanics. It's the atom. We're gonna go back to this in the course a little more, but atom, when they discovered that, okay, the atom exists, and we're gonna return it to atomistic a little bit to explain things. And then they start to say, well, okay, we know that there are plus and minus charge, and they know the electrons. Thomson discovered the electrons, and then they discovered the proton, and they must be together, making the atom. But how are they together? Rutherford, the brilliant British scientist, they discovered that the atom was something that was a nuclei. So Rutherford made the model of the atom as a nuclei and the electron around. That's the nucleated atom. And if we forget the electromagnetism we know, which is it's a great theory. It's a theory that survives even to quantum mechanics, even though it was formulated in classical basis, but it's wonderful. The electromagnetic, the explanation of light, and this is really wonderful. Okay, so if we forget a little bit about that, we can have an atom like an orbital model, electron going around the nuclei. That's true, we can do that. But if we introduce the electromagnetism, because it is a reality, we all know that exists. We see the light being formed, we see a charge generating fields. We're going to see that in that context, that when an electron goes around, it goes up and down, right? If you look by far, you see the electron, blah, blah, blah. And when a charge is oscillating, the field it's generated also oscillates. And the oscillation of charge generates an oscillating field, and that's its electromagnetic wave. It's light. So matter emits light. Well, that's good. We know that matter emits light. But that means that energy is lost, because this light, this electromagnetic wave, carries energy. So it turns out that the model that we think that the electron goes around, we can have by mechanical an orbital. You have a central force. It's like a planet going around the sun. But it loses energy because it has charge. And the electromagnetism requires that this emits charge. And then if it emits charge and charge and charge, the system collapses. And then you say, okay, well, it may collapses in 10 billion years or more than the age of the universe, and that you're wrong. If we consider the electron around the atom, we're going to see a collapse that takes 10 to the minus 11 seconds. So nothing could exist around us. We could not exist. So you see, even the simple things, which is how the electron and the nuclei are together, cannot be explained by the classical mechanics. Cannot be explained by the classical mechanics. And then Bohr, due to Bohr, and nobody else, he came with an explanation. He's saying that, look, in the atom, the electron is a wave. Wow. Here start to, that occupy the space without dissipation. That is really a different concept. If I come to you and say, look, when looking inside the atom, the electron is not like a particle that the Thomson detect. It's a wave. It's a wave that occupies the available space within the atom. And in that case, there is no reason why it should dissipate, because it is not really going around, it's occupying the space. Has many mechanical properties, angular momentum and everything, it will be there, but in a different context. Okay? And with that, he could explain many, many things, and was one of the important concepts to start quantum mechanics, is to say that electron is not always the way we think it is. And of course, we are all made of electrons, right? All the chemistry we have is electronic chemistry, it's not nuclear chemistry. Nuclei is only the mass, give us mass, but everything is electron going here and there and making chemical bonds, destroying chemical bonds, remaking chemical bonds, and so on. So, it turns out that if we consider the following experiment, here's an atom, following the Bohr idea. We have an atom, have this nuclei, which is tiny, and then have this cloud, which is a kind of wave that we're going to learn how to deduce, how to understand this wave, going around the nuclei. So this is around there. And then, you know that we can take electrons from atoms, right? We can ionize atoms. Suppose we ionize, pop, and we have around this, I have a single atom there. I have many detectors, but I have a single atom, and I'm going to do a single experiment. Well, if the electron was always this wave, and then when I ionize, I see this wave growing and reaching all the detectors. So each detector should detect a part of the electron. I have one atom, one electron, and I ionize the atom. I'm doing a kind of Gedanken experiment, okay? But it's doable. It's not even Gedanken. It's a real experiment you can do. But it's not what's happened. If you do this experiment, you're going to detect the electrons in one detector. So there is a real trajectory that the electron is going to take. But electron inside the atom is a wave. And that can explain many things we observe in the atom. But when I observe the electron by ionizing and detect, it looks like a particle. If it was a wave like this, we expect it like the wave in a swimming pool. The wave goes everywhere. So when we look at the electron, it looks like a particle, but inside the atom it's like a wave. So that is something very interesting in quantum mechanics, that the things, they are some way, but when I observe, they look like different. But to explain what is in there, we have to come with the concept of wave. And then, we pretty much accept that the electron is a wave when in the atom. But when I detect it, it looks pretty much like a particle. And that creates a concept that we use a lot, which is the duality wave-particle for the electron. That's an important concept. Nothing violates anything. It's just an observation, and I have to deal with. Right? I have to deal with this. And then comes the question. Using everything I told you, can we formulate a mathematical tool to deal with quantum mechanics, to deal with everything I told you? And the answer is yes. We can formulate, we can put a mathematics that makes sense for everything. And that's the quantum mechanics. That's the way we're going to do. And believe me, quantum science is both necessary and useful. And it has many consequences. Let me only flash some consequences of the quantum mechanics. Laser. Everybody knows about laser today. I'm not going to explain here the application, but laser can only be explained by quantum mechanics. No way out. You have to use quantum mechanics, right? All the so-called stimulated emission and everything that multiplicate light in the same way, so they travel together, they are equal, has to be done. And even the light has to be quantum, has to be packages, as we're going to see, to really be able to explain the laser. And they know, and that's how the laser was invented, because they understand, they apply, and they found. But many other things, quantum mechanics is applied. TV, the TV set, cellular phone, computers, and everything is product of quantum mechanics today. Color of nature, you know, the world around us is colorful. And to understand this color, we need quantum concepts. We need to know the light, we need to know the molecules, and we can understand why shining white light in an object, I reveal some colors, and sometimes I see darkness. What's going on there? Quantum mechanics can explain. Photosynthesis, can you imagine something more important than photosynthesis? Photosynthesis is this phenomenon of converting light into chemical bond. How that happens? People believe that, you know, people never really understood the photosynthesis because it's a so efficient effect. Almost 100% efficiency of light that the plant can take it. Not the one you shine, the one it can take it on a molecular level is transformed in chemical. And this is, people are really puzzled about how that happens. And I tell you, it's fully quantum. Today they understand a little better. Sense of smell. When you smell things, up to now people believe there was a kind of a key lock type of connection. You know, I have something here in a molecule that comes in the smell, what is the product, and then in my sense, I have a kind of a negative of that, and they come together, and I detect the smell. More recently, they discover that actually what's going on here is tunneling effect. Somehow this gets together, and the oscillation that produces the tunneling is what makes me to detect the smell. Wow, that's strange, but we're going to go to that. And many other things that happens that make us to really believe in quantum mechanics. I would like to explain to you some more effects, like the tunneling effect, like the tunneling microscope. Everything's fully quantum. You know, the tunneling microscope in the next door to this classroom, it is fully quantum. Electron can go tunneling the barrier and reveal the landscape of what I'm measuring is fully quantum. There is no way of doing classical. So you see, quantum mechanics is very important because we have to do things more efficient like photosynthesis. We have to detect the things. We have to make sensors that recognize single molecules. This is quantum. We have to understand and make new medication. This is quantum. We have to make devices that detects a few cells. When people has cancer, they have to find cells, and this, I believe, will be done in the quantum level. Okay, so we came to the end of this lecture on the introduction, and then from the next lecture we start our structure by explaining to you how waves behave, so we can make the good connection and understand the concepts of quantum mechanics. Until see you the next lecture. Bye bye.